Hello everyone. In this video, we shall discuss logarithmic functions and its graphs and its properties. But before we define what is a logarithmic function, let's recall first about an exponential function being a one-to-one function. So we know from another video that the exponential function f of x equals a raised to x is a one-to-one function. That is, if we have the equation a raised to x equals a raised to y, then it implies that their exponents are equal. Now, since the exponential function is a one-to-one function, then it means that it has an inverse function, an inverse function f inverse of x. So how do we get this inverse of an exponential function? So let's consider the basic exponential function f of x equals a raised to x. So what is the inverse of f of x equals a raised to x? So first we have to write it as y is equal to a raised to x. So we have to replace f of x by y. And then we interchange x and y. That's why we have x is equal to a raised to y. Now, in finding the inverse, we need to solve for the expression equivalent to the variable y. But to solve for y, we will be needing another concept. So we shall use logarithms. So hence, now to separate this exponent from the base, then we have to apply the logarithm of x to the base a. So the inverse of the exponential function of the basic exponential function is the logarithmic function f of x equals the logarithm of x to the base a. But the question is, how do we evaluate this logarithmic expression? So the expression log x to the base a is read as the logarithm of x to the base a. It is interpreted as to which value should we raise a so that the result would be equal to x. So for example, let's try to evaluate the following. We have the logarithm of 25 to the base 5. So to get the value of this without using our calculators, we need to think of an exponent which we can use for the base 5. And if we apply this 5 raised to that exponent, it should be equal to 25. So this means that if 25 is written as 5 raised to 2, then this value here must be equal to 2. So the logarithm of 25 to the base 5 is equal to 2. Now for the second one, the logarithm of 81 to the base 3. So we have 3 raised to something equals 81. But 81 is written as 3 raised to 4. So it's the product of 4 copies of 3. So which means that this thing is equal to 4. Now for the logarithm of 1 over 125 to the base 5, then this will be 5 raised to something is equal to 1 over 125. But 125 can be written as the cube of 5, or it's the product of 3 copies of 5. However, since the base is 5 here, then we have to use algebra to write this as 5 raised to negative 3. So this thing is equal to negative 3. Now for the logarithm of 1 over 9 to the base 1/3, then it should be that 1/3 raised to something is equal to 1 over 9. 1 over 9 is 1 over 3 squared, or it can be written as 1/3 raised to square. So which means that the exponent must be equal to 2. So the logarithm of 1 over 9 to the base 1/3 must be equal to 2. Now finally for the last one in this slide, if we have 1/2 raised to something equals 32, 32 can be written as 2 raised to positive 5. But since our base here is 1/2, then 2 raised to 5 can be written as 1 over 2 raised to 5, or it can be written as 1/2 raised to 5, because 1 raised to 5 is also 1. So which means this thing is equal to, I'm sorry, this should be negative, this should be 2 raised to negative 5. So this should be negative 5. So the value of the logarithm of 32 to the base 1/2 is equal to negative 5. So now if the base a is equal to 10, then we write logarithm of x to the base 10 as simply logarithm of x. Now we call this the common logarithm. So if the base a is equal to e, which is approximately 2.71, then we write the logarithm of x to the base e as ln of x. And we call this the natural logarithm. So to evaluate these logarithms, now having the base 10 and base e, let's have the following. Let's evaluate the logarithm of 100. So this means that 10 raised to something is equal to 100, while 100 can be written as 10 squared. So which means that this logarithm is equal to 2. For the second one, we have 10 raised to something equals 1 over 10. And 1 over 10 can be written as 10 raised to negative 1. So this is equal to negative 1. Now for the third one, we have 10 raised to something is equal to 0.001. And this 0.001 is actually 1 over 1000, which is 1 over 10 raised to 3, or it can be written as 10 raised to negative 3. So which means that this is equal to negative 3. And then for the fourth one, so this means that the base is e. So e raised to something is equal to e raised to 3. So obviously, by the one-to-one property, ln of e raised to 3 is equal to 3. And then for the last one, e raised to something equals 1 over e. And 1 over e can be written as e raised to negative 1. So which means that this state is equal to negative 1. So that's how we evaluate the logarithms whenever the bases are 10 and e. Okay, next. So another concept that you need to know about the logarithmic functions is you should know how to convert the exponential to the logarithmic form. So if we're given with the exponential form, x equals a raised to y, then it can be converted in logarithmic form as follows. So the exponent will be separated from the rest, and then we get the logarithm of this one, which is x, and then the base will be used as a subscript of the logarithm. So for example, let's convert the following to logarithmic form. So we have 2 raised to 5 equals 32. So that means the exponent is separated from the rest. And then we have the logarithm of the other side, which is 32. And then we shall use the base 2 as a subscript of the logarithm. Now for the second one, the exponent is z. So we can write this as z is equal to the logarithm of the other side, which is the quantity of 3m minus 5. And then since the base is 10, we may opt not to write it in this expression. So it's obvious that whenever we have the logarithm without base, the base must be 10. And then for the third one, the exponent is 4, so we separate 4 from the rest. Since the base is e, we shall write ln, and then it's ln of the other side, which is z. So that's how we convert exponential form to logarithmic form. So this conversion thing can be applied whenever we find the inverse of an exponential function. So let's find the inverse of f of x is equal to 2 raised to x plus 3. So first, let's write this as y is equal to 2 raised to x plus 3. And then we interchange x and y. So we write this as x is equal to 2 raised to y plus 3. And then at this point, we need to convert into logarithmic form in order to separate y plus 3. So when we convert it, it will become y plus 3 is equal to the logarithm of the other side, which is x, and then using the base 2. So if we solve for y, we transpose 3 to the other side. So y is equal to the logarithm of x to the base 2 and then minus 3. Or we can write this as negative 3 plus the logarithm of x to the base 2. So this is the inverse of this function. Okay, next, let's find the inverse of f of x equals 1/4 raised to x minus 2. So again, let's write this as y is equal to 1/4 raised to x, and then we have the minus 2. So interchanging x and y, we write it as x is equal to 1/4 raised to y minus 2. And then we have to transpose the negative 2 to the other side first. So we get x plus 2 is equal to 1/4 raised to y. So in order to separate y, since we are solving for y, we need to convert this exponential form into logarithmic form. So y is now separated from the rest, and then we write the logarithm of the other side, which is x plus 2, and then using the base 1/4. So this is the inverse of 1/4 raised to x minus 2. Okay, so for another example is whenever we have f of x equals 3 raised to x minus 2 plus 4. So we write this as y is equal to 3 raised to x minus 2 and then plus 4. We interchange x and y. So we write it as follows. And then we transpose 4 to the other side. So we get x minus 4 is equal to 3 raised to y minus 2. So at this point, we need to convert into logarithmic form by separating y minus 2 from the rest. So it must be the logarithm of the other side, x minus 4 to the base 3. So uh, this is the inverse, but we need to transpose the negative 2 to the right side. So we write it as y is equal to 2 plus the logarithm of x minus 4 to the base 3. So this is the inverse of this function. So this is our f inverse of x. Okay, now, so since you already know how to get the inverse of exponential functions, we are now ready to define what are logarithmic functions. So since logarithmic functions are inverses of exponential functions, we shall be having the base a. So the base a is still a positive real number that is not equal to 1. And the logarithmic function with base a written as log of x to the base a is defined by y equals the logarithm of x to the base a if and only if x is equal to the base a raised to the exponent y. So this is the definition for every x greater than 0 and every real number y. So which means here that x should be positive. X should be greater than 0. It means that this parameter here must always be positive. It cannot be 0, it cannot be negative. So which means if you're going to evaluate the logarithm of, let's say, negative 1 to any base, any positive real number base that is not equal to 1, then this doesn't exist. So there's no value here. So this is an error. Okay, so note that the inverse of the exponential function f of x equals a raised to x is the logarithmic function f inverse of x equals the logarithm of x to the base a. So to sketch the graph of these logarithmic functions, let's consider the graph of f of x equals the logarithm of x to the base 2. So in this case, the base is equal to 2, which is higher than 1. So this function is actually the inverse of the basic exponential function 2 raised to x. So in order to graph this logarithmic function, we can just simply interchange the x and the y coordinates of this exponential function. So which means that the ordered pairs for the logarithm of x to the base 2 are as follows. And these are just the result of interchanging the x and y coordinates of 2 raised to x. Okay, so now, for the graph of this logarithmic function, we show first the graph of the basic exponential function using the following points. Okay. So whenever we have the point negative 2 comma 1/4, if we interchange the x and y coordinates here, we are going to get 1/4 comma negative 2, which is this point here. If we interchange the point negative 1 comma 1/2, we will get the point 1/2 comma 1. 1/2 comma negative 1, I'm sorry. And then if we have 0 comma 1 for the exponential, then if we interchange this ordered pairs, then we get 1 comma 0. And so on and so forth. So 1 comma 2 when interchange will be 2 comma 1. 2 comma 4 when interchange will become 4 comma 2. So hence, these points here are the points of the logarithmic function, logarithm of x to the base 2. Now, since the graph of the logarithmic function is just obtained by interchanging the ordered pairs of the points of the basic exponential function, then the properties of the logarithmic functions will just be based on the properties of the exponential function. So that means the domain and the range of the exponential function will be interchanged to get the domain and the range of the logarithmic function. So since in exponential functions, the domain is the set of all real numbers, then in the logarithmic function, it will now be the range. Now in exponential functions, y is always greater than 0. Now since we interchange x and y, then that means in logarithmic functions, x must be greater than 0. So that's the domain of the logarithmic functions, or the basic logarithmic function. Now, in the basic exponential function, the y-intercept is 0, 1, and the x-intercept is none. So which means that this will just interchange, and as well as we interchange the coordinates of 0 and 1. Now, since a, or the base, is higher than 1, it's still an increasing function. And we know from exponential functions that it has a horizontal asymptote. So therefore, in logarithmic function, the horizontal asymptote will become the vertical asymptote, which is the y-axis, or x is equal to 0. And since the exponential function is 1 to 1, then its inverse, which is the logarithmic function, will also be a 1 to 1 function. Okay, next, let's consider this time the graph of the logarithmic function whenever the base a is between 0 and 1. So let us graph the f of x equals the logarithm of x to the base 1/2. So since the given function is the inverse of the basic exponential function g of x equals 1/2 raised to x, we just interchange the x and y values in the following table. So this is the table for g of x equals the exponential function 1/2 raised to x. So if we interchange these ordered pairs here, we get the following ordered pairs for the logarithm of x to the base 1/2. So plotting the points of the logarithmic function. So let me show you first the graph of the basic exponential function 1/2 raised to x. So if x is negative 1, the value of y is positive 2. If x is 0, the value of y is 1. If x is equal to 1, the value of y is 1/2. If x is equal to 2, the value of y is 1/4. So if we interchange the coordinates of these points, then we get the following. So for negative 1 comma 2, if we interchange this, we get 2 comma negative 1, which is this point. 0 comma 1 when interchanged will become 1 comma 0. 1 comma 1 half when interchange will become 1 half comma 1. 2 comma 1 fourth when interchange will become 1 fourth comma 2. So we have these points on the green graph as the points for the logarithm of x to the base 1 half. So the properties of this logarithmic function where the base a is between 0 and 1, so is actually the same as the properties whenever the base is higher than 1, except that whenever the base is between 0 and 1, the graph will be a decreasing function. Okay, let me change this first. Okay, so in logarithmic functions where the base is between 0 and 1, the graph is a decreasing function. But all the rest of the properties will be the same. Now, since the logarithmic function is also a one-to-one function, that means that whenever we have the logarithm of x to the base a equals the logarithm of y to the base a, that means that their parameters x and y must be equal. So whenever we have the logarithm of, let's say, x to the base 2 is equal to the logarithm of a to the base 2, this means that x is equal to 8. So now, so this one-to-one property can be used later on in solving for logarithmic equations. Now, so since you already know the properties and the graphs of the basic logarithmic function, now this time, let us study how to convert logarithmic forms to exponential form. So if we are given with a logarithmic form, y equals the logarithm of x to the base a, then it can be converted in exponential form as follows. So this means that the base a must be raised to the exponent y, and it will be equated to the parameter x. So in here, to convert this in exponential form, so we use the base form, raise it to the value at the other side, and then equate it to the parameter, which is 64. For the second one, we use the base 2, we raise it by the value at the other side, and equate it to the parameter, which is x plus z. So this is how we convert the logarithmic to exponential form. So now, so that technique of converting the logarithmic form to exponential form can be used to find the inverse of the logarithmic function. So let's find the inverse of this logarithmic function. So first, we write it as y is equal to the logarithm of x plus 2 to the base 5. So again, in finding the inverse, we interchange x and y. So we write it as x is equal to the logarithm of y plus 2 to the base 5. So solving for y, we have to convert this to exponential form. So we write it as the base 5 raised to x equals the parameter, which is y plus 2. And then solving for y, we need to transpose positive 2 to the other side. So we write 5 to the x minus 2 is equal to y. So this is the inverse of this logarithmic function. So let's have another one. Let's consider the inverse of f of x equals the logarithm of x plus 8. So first, we write this as y is equal to the logarithm of x plus 8. And then we interchange x and y. So to solve for y, we need to transpose the 8 first. So we get x minus 8 is equal to the logarithm of y. And then at this point, we convert to the exponential form. So since the base is not written, obviously the base must be 10, and we raise it to the other side, which is x minus 8, and then equate it to the parameter, which is y. So this is the inverse of this logarithmic function. And then let's have another one. So let's find the inverse of f of x equals ln of x minus 3 minus 2. So let's write this first as y is equal to ln of x minus 3 and then minus 2. And then we interchange x and y. So we have the following equation. So to solve for y, we will transpose negative 2 to the other side. We get x plus 2 is equal to ln of y minus 3. And then at this point, we will convert into the exponential form. So since this is ln, the base must be 2, we will raise it to x plus 2 and equate it to the parameter, which is y minus 3. And then we will transpose the negative 2 to the other side. So we have e raised to x plus 2 plus 3 is equal to y. So this is the inverse of ln of x minus 3 minus 2. So now, so since you already know the graphs of the basic logarithmic functions, now this time let us try to graph a logarithmic function that would involve horizontal and vertical shifts. So let's consider the function g of x equals the logarithm of x minus h to the base a. So the graph of g of x can be obtained by just shifting the graph of the basic logarithmic function, logarithm of x to the base a, by h units to the left if h is less than 0. Now, if h is greater than 0, then the graph of the basic logarithmic function will be shifted by h units to the right. So for example, if we are going to graph g of x equals the logarithm of x plus 1 to the base 2, then we have to determine the value of h. So in this case, x plus 1 can be written as x minus negative 1, which indicates that h is equal to negative 1. So that means the graph of the basic logarithmic function, logarithm of x to the base 2, must be shifted by 1 unit to the left. So which means that these points here must be shifted by 1 unit to the left. So we have the following points. Okay, so this means that the vertical asymptote of the basic logarithmic function will also be shifted by 1 unit to the left. So that's how we graph logarithmic function having horizontal shifts. So if h is positive, then the graph of the basic logarithmic function will be shifted by h units to the right. Now, for the vertical shift, if we consider g of x equals logarithm of x to the base a and then plus k outside, the graph of g of x is obtained by shifting the graph of the basic logarithmic function by k units downward if k is negative. And if k is positive, the graph of the basic logarithmic function will be shifted by k units upward. So for example, if we are going to graph g of x equals the logarithm of x to the base 2 plus 2, then this means that the graph of the basic logarithmic function will be shifted by 2 units upward. So which means that these points here will be shifted by 2 units upward. So this is the graph of the logarithm of x to the base 2 plus 2. So if we would combine both horizontal and vertical shifts, then we have g of x is equal to the logarithm of x minus h to the base a plus k. So the graph of g of x is obtained by shifting the graph of the basic logarithmic function by h units horizontally and then followed by k units vertically. So if we have the logarithm of x plus 1 to the base 2 plus 2, this can be written as the logarithm of x minus negative 1 to the base 2 plus 2. So this indicates that h is equal to negative 1 and k is equal to positive 2. So which means that the graph of the basic logarithmic function will be shifted by 1 unit to the left and 2 units upward. So which means if we have these points from the basic logarithmic function, these points will be shifted by 1 unit to the left and then 2 units upward. 1 unit to the left, 2 units upward. 1 unit to the left, 2 units upward. So we have this graph of this logarithmic function. Okay, next, now whenever we have g of x is equal to the logarithm of negative x to the base a, and g of x is equal to the negative of the logarithm of x to the base a, then we have the following. The graph of logarithm of negative x to the base a is just a reflection of the graph of f of x equals the logarithm of x to the base a along the y-axis, while the graph of the negative of the logarithm of x to the base 8 is the reflection of the graph of the basic logarithmic function along the x-axis. So in here, if we are supposed to graph logarithm of negative x to the base 2, then we shall only reflect the points of this basic logarithmic function along the y-axis. So which means this point will be reflected and its mirror will be this point. This point will be reflected to this point, and this point will be reflected to this point. So this graph here is the graph of g of x equals logarithm of negative x to the base 2. And then if we have g of x equals the negative of logarithm of x to the base 2, then the points of the basic logarithmic function will be reflected along the x-axis. So which means that this point will be reflected to uh, this position. This point will be retained in this position, while this point will be reflected here. So curve here, this curve here is the graph of g of x equals the negative of the logarithm of x to the base 2. Okay, so now, since you already know the graphs of the basic, exponential, and the basic logarithmic functions, and we know that they are inverses of each other, then we can now say that the graphs of these basic exponential and basic logarithmic functions are symmetric with respect to the line y equals x. So it is shown here that this one is the graph of 2 raised to x. This one is the graph of the logarithm of x to the base 2. And these two graphs are being reflected by the line y is equal to x. So the other properties of the exponential and logarithmic functions shall be discussed in the next video. And this ends our discussion of the logarithmic function. So I hope that you learned something from this video. And please do not forget to subscribe to my channel. Thank you for listening.